Welcome to the Eduonics Projects in Hadoop course. In this video segment, we are in part 1, Add Value to Existing Data. In this first part, we are really going to get going with Mapreduce and learn Hadoop and Mapreduce concepts in the context of problems that we will solve. And the motivation for big data largely came from adding value to existing data sets. In terms of the commercial success, it really gained a lot of momentum when big corporations discovered they could add value to their existing data. So that's what we're going to look at in the context of a practical problem that we will solve. And the concepts that we will get on top of while we solve this practical problem are 1. Mapreduce, shuffle sort, and what's known as natural language processing, or NLP, entity extraction and clustering. So we're going to start from where it all begins with Mapreduce and then move on to something that's quite advanced. In this first part, we're looking at how we can leverage data that previously might not have had any value. But with the advent of this technology, now we can extract or harvest value from that data. Previously, the sort of data that was just lying around that might not have seemed to be of value were things like access logs, error logs, comments on blogs, and some types of database content. Now we can come back to this data and look at it as being valuable. Let's look at a problem scenario. Imagine we are a small business, we're a marketing business, and we're going to create a marketing campaign based on a database that we've been given access to. We want our campaign to be professional, and in particular, we do not want to send out 2 copies of our marketing materials to any one business entity. So we need to mine through this financial services database and check that we have unique addresses for each name. So now we have set up our problem scenario. Let's move on and look at what our data looks like. So we're going to work with 2 data sets. We're going to work with a small data set of just a few hundred lines of data. This is for testing and development. We're going to select from the bigger data set, when we create this smaller data set, a few more duplicates within this smaller data set than what would be found inside the larger data set. Now our duplicates are going to be when we have the same key value. So let's have a look at an example of our data and what we call a key value. So this is what a row in our data looks like. We can look at the address field here, and you can see this is problematic. This is where a lot of the problems come in US data, is their address fields are so large. So if we look compared to this to the Norway, here we have a bank in Norway, and its address is really small. But if we look at a bank somewhere in the States, you can see we have these big address fields. That will be the problem, because sometimes these big address fields will be for the same address, and that's what we want to eliminate. So the first step is to try and cluster this data. So we aggregate all the key values. So here I've highlighted the key values in red. So we want all these key values that are the same, and then we want to collect all the address fields for the same key value. So if we have one key value with many address fields, then we can have a high probability that there is a duplicate address, that we have an address that's the same, it just looks different. And that's the problem we want to try and eliminate. So the first step is to mine through this data, and every time we end up with a duplicate key, this key value here that I've highlighted in the red, then we collect just one value of that key and we collect the aggregate values of its address fields. And then in a further application, which we will develop later, we will work on these address fields and write some clustering code that will decide if these address fields are actually the same. So the first step is to collect all the keys that are the same and aggregate their address field. So let's have a look. We'll step through the code. Here we have the directory structure of the code. It's a standard Maven project. So we have a source directory, target directory for our build files. Then we have our output directory for our Uberjar. And then at the top level project, we have our POM build file. This is the build file for Maven, pom.xml. And then we have our data sets. We have our small data set with more duplicates than usual for testing. Then we have a large 10,000 line data set that comes from the actual commercial database. So this is our directory structure. So what we'll do now is we'll step through the source code. What we're going to do now is step through the important parts of a source code. Now this is not a theoretical course. This is a problem-based learning course where we look at Hadoop in different domain areas, and we focus on the key aspects of the code that solve the issues to successfully implement the solutions. So we're starting with the build file, so how we build the project. This is critical, and this is where a lot of the really difficult errors can occur when you are dealing with the dependencies you need to get your code to work. So the first thing to point out is we are using the latest version of Hadoop 2.7.0. So you need to run this code on a cluster that supports the latest version of Hadoop. And then we have a minimal set of dependencies because this is just a fairly minimalistic Mapreduce job. There's not a lot of other applications or artifacts running in this code. It's very much pure Mapreduce. We have our Hadoop file system dependency. We have our Hadoop client. So we have two Hadoop dependencies. It's very important that when we build the code, we're building it at the source level that the cluster requires. So Java 8 is pretty standard now, so we need to make sure we're building at the source level 7 because the cluster will be running at that source level. Then we use the Shade plugin to build what's known as the Uber jar. This is the big jar that contains all the dependencies that the code will need when it runs in the cluster. Here we're declaring the main class for the code. We need to declare this services resource transformer in our Shade plugin to resolve issues with the file system. When we pull in these dependencies, we will end up with various versions of the file system classes. And what this line does here is it resolves all the versions of the file system classes that are on the class path to a single version resource. So if this line is not included, later on we will get exceptions. And this is a utility plugin which will copy the Uber jar. It will copy that from the project build directory, which is the target directory, and it will copy it to our staging directory for this code, which is Uber jar at the top level of the source. So that's our build file. This is the main class that will run our Hadoop job, and this is declared as the main class in the Shade plugin so that we can easily run it from the jar. And in the new Hadoop 2.2 Plus framework, we extend the superclass configured and we implement this interface tool. Then we can get things running in our main method using the tool runner static method run. And we declare our configuration and an instance of this class, and we pass in the arguments to the code that come in when we initiate the main method from running the jar. And when the job is finished successfully, it will shut down. When we implement this tool interface, it requires us to create this run method. And so this run method will be called by the tool runner. We need to have a path set up. So we don't know where this jar is going to be run, so we can't use hard-coded absolute paths. We need to make all our paths relative. One way to do that is by using the system-get property user directory, and that will pull in an absolute path to where the jar is located. So we don't need to set that absolute path in the code. And then we can build everything relative to this path, creating strings where we have the name of our file that we want to run. We have the output directory. Now we're appending the system time to the output directory. When we are developing the code, when we run it repeatedly, if the output directory already exists, we will get a runtime exception. So this allows us to run repeated iterations of this main class. Now we create our path objects. Now it's important to point out that these are not Java NIO paths. These are part of the Hadoop framework paths. So let's have a look at where we're using these artifacts. So we get our configuration, we create our output paths, so they are relative to wherever the jar's location is. We create an instance of the job. In the context of this code, this job type we have created here is a Hadoop Mapreduce job. But we can think of jobs at a higher level because we have other frameworks like batch frameworks or cron frameworks where we also have jobs. And we can think of a job as a task that can be scheduled to run repeatedly or once in responds to a change somewhere. So a job exists at many levels. Here it is a Mapreduce job, but it's important to understand it's very similar in its high-level architecture to a batch job. It's something that can be scheduled. What follows are standard Mapreduce configuration artifacts. So firstly, we set the jar, the runtime jar, which has the main class, and then we set two classes, the mapper class and the reducer class. In this code, the mapper and reducer classes are inner classes, which we'll go through in a minute. When we run this code, it mines through the data set and aggregates all the keys, and when you have two keys the same, it combines them to a single key, but it aggregates their values. The step that does that is sometimes known as a shuffle sort step. And what we configure here are the types, the inputs and the output types for these steps. And the text.class is equivalent to the Hadoop string method. So the output for the shuffle sort is going to be of string type. Then we configure the paths for the job. Then we wait for the job to complete. When it's finished, we exit cleanly. So now what we'll do is we'll step through the mapper and the reducer code. Here, to create our mapper class, we extend Hadoop's mapper type, where we have input fields. The ones we're concerned about are this field here, text, which is a string. This represents one line in the file. So here we are, getting the actual line or the record in the input file. And then these are output types, which we output to the Hadoop system to magically be processed in the shuffle sort step. It has this input key and the input value, which represents one record of our input data, and a context type. We can think of this as our bridge to the magic of Hadoop. We can put things into the context, get things out of the context. We can process data into the context, into the shuffle sort step. So we emit a key and a value into the Hadoop flow inside our map method. It's up to us to define what will be the key and the value that we pass on via the context to the shuffle sort step. So firstly, we obtain the record, and it's a tab delimited file. So we split on the line an array of strings that we can work with. Now here we are just processing the header. Then we just extract the key that we want. So it's a second value in the tab delimited string, and the whole line itself will be the value line. And we emit these to the shuffle sort step. Then in the reducer, these come in. So here we have the input. So what we are outputting here in terms of types coming into our reducer. Now in the shuffle sort step, all the keys that are the same are aggregated to a single key, but then they will have many value lines. We take advantage of that to process the duplicates. We can look at how many values do we have in our input. So if we had a situation where we had two keys the same, the size of this iterable would be 2. So this count tells us how many duplicates we have for any given key. So that's a very small amount of code to do something that's actually quite involved. Now if we have duplicates, that is, we have more than one value for a given key. If we have duplicates, then we process them as duplicates. So we just flag we've got a duplicate, we do whatever we want with it. So here we're just flagging and listing the actual strings that are the values for that particular key where there are duplicate values. And then we emit that to the context. Now from the reducer, the context is going direct to the file system. So what we emit from the context here will go into the file system. If we have duplicates, then we write our duplicate line. If we don't have duplicates, we just write our standard line. So this int writable here will be how many values there were for the given key. So this, via our entity reducer and our entity mapper, is how we can mine through our data, discover the duplicate key values, and then collect or aggregate all the lines where there is a duplicate key, and that will be our output data. Now we can process and output the data in various schemes and formats. So at the moment we're just doing it in such a way that it flags the fact that duplicates exist and shows the duplicate line values. Now that we've stepped through the code and we understand the code flow, we'll move on and we'll build the code and run the code locally from a jar and test the code running from a jar on different data sets to check that everything is working. Welcome to the Eduonics Projects in Hadoop course. In this video segment, we are in the second part of Part 1, Add Value to Existing Data. So now we're going to build and run the code. So the first thing is to check for this test that we are using the small version of the input data. We could build and run the code inside our IDE. In this case, it's IntelliJ, or it could be in Eclipse, but to make it more cross-IDE friendly, we will just run it from the command line. So we're going to issue inside a terminal, inside the top level source folder at the same level as the pom.xml, the Maven build commands Maven clean package. And if we scroll down here, we can see that the directory where the uberjar will end up is empty, so we're going to build a new uberjar to run the code. So let's run that build configuration. So now it's running Maven clean package, and it's important to remember I've set the source code output level as 7, because when it runs in the Hadoop cluster it's going to run as Java 7. So here we can see we have build success. So we'll go down now, we look in the directory for the uberjar, and we can see we have created the uberjar. So what we need to do now is just run the uberjar, and it should find the actual input files that it wants to use in its directory that it lives in. So let's do that now. Now we've used the system property, user directory, so that will set the absolute location for the code as being the directory it exists in. So we'll look inside this directory for its input file, and we are using the smaller input file which has more duplicate key values, because we want to check we are picking up those duplicate key values when we run the code from the jar. Change to the directory that the jar is residing in, and we just run it simply with java-jar and in the name of the jar ubu.jar. So we run the code and it'll quickly pass through the files. Now if we check in our directory, we will see inside the same directory that the jar was in, we have this output directory with a timestamp, and we can open up the output. And if we make this bigger so we can see what's happening, we're looking for duplicates. So here's our first duplicate values. We found some for this company. Now if we move on down, we should find a lot of duplicates because I optimized this particular input data set to have many duplicates. So it's finding all the duplicates. What we'll do now is we will rebuild the code. What we'll do is we'll change to the big version of the input data. So that's our big data input. So now, as you can see, we have not deleted the uberjar, because when we build again, it will copy over and overwrite the existing uberjar. But if you're worried that it might not be doing that, you can always delete the uberjar if you want to. So now we've changed the name of our input data file to be the 10,000 line data file. So we rebuild the code. So when we run the jar, it will reflect the latest value. So when it's doing this section of the build, it's downloading everything to go inside the uberjar. So now we change into the directory where the uberjar exists. So now we're in the terminal directory where the uberjar exists. We're going to run the uberjar again. So we run it again with the big data set. We expect it to take a bit longer this time. Now we notice it seems to be about the same amount of time. So when we run the 200 line data set or the 10,000 line data set, a lot of the time that we're seeing here is just initialization of our pseudo cluster. You could see it could easily handle very big data sets. So Hadoop is a great framework. It's a great way to be doing this sort of clustering code. So now we look for the output that has the latest timestamp. So here we are, 922 is greater than 459, so this will be our latest result set. Now if we go through, we can see for the 10,000 line data set, there are not many duplicates. Now what I did was when I set up my small data set, I deliberately chose sections of the data that had a lot of duplicates because I wanted to check that I could find the duplicates easily. But now this larger 10,000 line data set is a more original, faithful to the original database where this data came from. So there are much less duplicates. But if we go down, we'll be able to find some duplicates eventually. So here we are. So here we found 3 duplicates for AXA Advisors Limited Corporation. So now we've successfully built and run the first phase of our code, and that is creating Mapreduce code that gets that key, then using that key value, looks for duplicates via the shuffle sort step, and so for each unique key it will aggregate the values for that key. So we get this almost for nothing in Mapreduce. If we were to write equivalent Java code that mined through all the 10,000 lines, created a list with all the keys, and then recursively mined through the data set again, finding duplicate values for those keys, that would take much longer and be much more code than what we have produced here. So this is a very good way to use Mapreduce to find duplicates and also to find initial seeds or centers for our later clustering algorithm to come. Now we will go through the steps to run the code in Hadoop, highlighting the important steps as we go along. So we need to boot up the Hortonworks virtual machine, and it shows you the credentials in its landing page. Then in a terminal we can access the machine with this URL, and the password is Hadoop. Now we are logged in. If we look what we have in the root directory, because we land in the root directory, we can see we have already copied over our ubu.jar and our data set. So we have our 10,000 line data set, and we have our ubu.jar. Now we can confirm this by looking in an SSH file browser. So here I've also connected with an SSH file browser, so I can easily copy in my ubu.jar and my data set. So they're all set up, ready to go. That's the first step. Now the next step is to log in on the virtual machine as the HDFS user. So we'll do that now. We'll just log in HDFS user. So now we're logged in as the HDFS user, and we have all the correct permissions that we need to access the HDFS file system. The next step now is to create a root directory. So we need to run this command to create a root directory. And I've previously run this command. So we'll have a look what's in our root directory. So here I am LSing the root directory, and it should be empty. So we're just waiting for HDFS to report back. And I actually have, from a previous run when I was checking the code would work, an output directory. So I want to get rid of that output directory. So if I go here, this is a command that will get rid of that output directory for me, but its actual timestamp is a little bit different, so I'll copy it. So I'll make a copy of that command and I'll paste it in here. So now I've got the correct timestamp, and I'm going to run this command to get rid of that output directory in the root directory. So I previously created a root directory off the top level directory, and now I've run that command. So let's check now what we've got remaining in our root directory. So now I'm LSing my root directory, and I'm hoping that my root directory will be empty. Yes, my root directory is empty, so I can start with a clean slate. So my next step is to use the HDFS to copy in the files that I need. So a good place to get started with HDFS file system commands is this link here. So you can find many examples of HDFS transfer commands here. So the first thing is to give the permissions to the root directory. I need to give it read-write permissions. Before I can copy or run anything in my newly created root directory, I need to make sure it's got all the permissions for read and write and execute. So this is a command that does that. So I execute this command, and all these commands are in the documentation here. Then the next step will be to copy over the files that we need. So I need to copy over the data file and the syntax, put, name of file, then destination that the file will go to. So now with everything in place, I'm ready to run the jar with Hadoop space jar space name of jar, which is ubu.jar. So we run that and we hope that everything works out. So it needs to be able to find the files. So recall we set up the system.dir, the root directory. All the paths in our application are relative to the location of a jar, and you can see it's running the job. If it gets that far, it generally means that it is working out okay. Okay, so now it's starting on the Mapreduce phase. You can see map there 0%. Now it's mapped 100%. It's into the reduce phase, and the reduce seems to be a little bit more work, so it's taking a bit longer. That's where we're aggregating the keys. Did the job work? So we read through. We're looking for errors. So we don't see any errors, so everything looks good. So our Hadoop job ran. So all we need to do now is get the output out into a place where it's useful. Where you will find you generally have errors with Hadoop code is in the paths. So resolving the path from where your code is running to where the other artifacts like input files and output files that the code needs, this is where the errors will be in the paths. So if you get the paths right, Java is fairly easy language to work in. So once you get the paths and the cluster set up correctly, everything is very solid and robust in Hadoop. So now we need to get the data out of HDFS. So the same way we put the data into HDFS, we can use the get command to get the data from HDFS. And we know we're going to be in an output directory that looks something like this. It will have a timestamp, so we can just use the wildcard there to grab output star, and it will match to the single output directory that will match on the timestamp. And then destination for our get is actually our source directory or our root directory. So try that output. Now let's have a look in our file browser. So we've got our file browser here. Do we have an output directory there? So we'll just refresh this by changing to something. We need to read, and there's our output. So now we're in the root directory of a virtual machine, and you can see we have the output. And this is where the SSH file browser makes life very easy. If we look here in the output, open with gedit. This is the output data, and we can see it's the same as when we ran it locally with a test. Not that many matches, so we just need to go down for a while. So here's our first duplicate. So we ran it in Hadoop on 10,000 records, and the code worked out. So what we need to do now is upgrade our code a bit so we can set it up to be useful for clustering. So what we need to do is output these duplicates and use them as seed clusters for further clustering. Let's just summarize the key steps involved in running the code in the Hadoop cluster. Firstly, we needed to boot up the Hortonworks virtual machine and then log in using this URL. That's our username, and this is the URL for an SSH session in a terminal. This is the password. And then we need to work with the HDFS or the Hadoop file system. So here's a link with lots of useful information about getting started with HDFS. The first thing we need to do is log in as the HDFS user in the virtual machine so that we have the HDFS permissions. We need to resolve the paths correctly with respect to the local file system. We are running the jar from Hadoop, so our jar is running on the local file system in the VM. We need to resolve the HDFS URLs correctly, so that means we need to create a root directory. So in the Hadoop file system we create a root directory, and we need to give that all the permissions it needs, reads and writes. We need to put the data into that directory. In the local file system in the root directory, we issue this command which runs the ubu jar in the Hadoop cluster. Then once it's finished, we need to be able to get the output. So we can use the Hadoop get command. And then finally, when we want to clean up, this is a command we can run to delete the output directories in the Hadoop file system. So if we replace that with a wildcard, it'll pick up the output directories and delete them. So there's a summary of the critical steps. And to repeat, generally when you have problems, it's going to be with paths. Resolving the paths correctly in Hadoop can be a challenge. So what we'll do now is we'll move on in the next part and we'll look at creating the add-on clustering code. So now we've found the duplicates, let's see how we can modify our Mapreduce code so it outputs the duplicates, and then we can use those duplicates as seeds for a clustering algorithm to cluster on the data.